Every day, millions of vehicles move across the UK's road network, leaving behind an invisible trail of exhaust. To manage this, the government sets a strict legal limit for nitrogen dioxide, or NO2, a toxic gas linked to respiratory issues. The limit is 40 micrograms per cubic meter, or UG per m cubed, which measures the weight of the gas within a specific volume of air. To find where the air is illegal, national agencies rely on massive computer models to predict concentrations across entire cities. These national models operate at a macro scale. While they are useful for broad trends, they often miss the hyper-local realities of a single street corner or a specific bus stop. The only way to see what a pedestrian is actually breathing is to use a diffusion tube. It is a simple plastic cylinder, usually zip-tied to a lamppost at head height. An environmental health professional uses these tubes to collect physical air samples over several weeks. This process provides a grounded, empirical baseline that a software simulation can only estimate. Supercomputers can guess at the big picture, but verifying legal compliance requires this kind of physical, street-level monitoring. These tubes are placed in every environment imaginable, from the dense, enclosed streets of central London to the wide, multi-lane expanses of the M25 motorway. Inside each tube is a chemical that traps NO2 as air passes through. After a month on the street, the tube is sent to a lab to calculate the period mean concentration, which is the average level of pollution at that exact spot over time. When scientists compared data from tubes placed at different distances from the same road, they found that NO2 doesn't dissipate evenly. It doesn't drop off in a straight line. Instead, the data reveals a steep mathematical plunge. The concentration of NO2 reduces linearly against the natural logarithm of the distance from the curb. This is known as logarithmic decay, a pattern where the most dramatic drop in pollution happens in the first few meters, before the rate of change slows down as you move further away. This chart shows how scientists use a specific formula to predict that decay. By taking one measurement from a tube at the curb, they can use this math to calculate exactly how much the air quality improves as you move towards the buildings behind it. The math shows that while the air at the very edge of the road might be at an illegal 60 micrograms per meter cubed, the concentration can drop below the legal limit of 40 micrograms per meter cubed, just 5 meters away at a building's facade. Proving this rapid decay curve is essential for accurately measuring how much pollution people are actually exposed to in their homes and workplaces. This empirical curve creates a problem for standard national screening models, like the Design Manual for Roads and Bridges, or DMRB. When we compare them, the computer models are often too conservative. The DMRB model predicts a much shallower decline than what we actually see in the physical data from the tubes. This inaccuracy means local authorities might over-predict pollution levels at a house 5 meters from the road, leading to unnecessary restrictions or public concern based on flawed math. Even advanced software like ADMS Roads has its limits. While it's more accurate than older models, it still struggles to perfectly map the first 20 meters from the curb, often predicting a shallower initial drop than the tubes actually record. Without physical monitoring to correct these algorithms, cities risk making multi-million-pound policy decisions based on a distorted view of the air quality. When a diffusion tube proves that a street segment is consistently exceeding 40 micrograms per meter cubed, the data transitions from a lab report to a legal trigger. This empirical proof of a breach legally requires the local authority to implement measures that bring the area into compliance in the shortest possible time. The first major result is often a bus retrofit program. In cities like Dudley and Portsmouth, this data has led to the upgrading of hundreds of buses to Euro VI standards, a strict regulation that forces engines to use advanced filters and catalysts to neutralize NO2 before it leaves the tailpipe. In Sandwell, the same data led to signal optimization. By adjusting the timing of traffic lights, engineers can reduce the time cars spend idling, which prevents the buildup of the dense pollution pockets captured by the tubes. In other cities, the data justifies more direct intervention, like pedestrianizing shopping streets or creating low-emission zones that remove the most polluting vehicles from the area. For an environmental health student, the work of swapping out these tubes is the foundation for these large-scale municipal changes. Placing a plastic tube on a lamppost provides the physical evidence that requires a government to change its infrastructure and protect the health of its residents.